Okay. Now we come to some interesting things here. We're gonna go back to our hydrogen atom, and we're gonna do some estimates now. Here I have to start the thing with a pretty big caveat. These are order of magnitudes estimates. They are not exact calculations. The intention here for you is to understand the properties, and particularly the lifetimes. And we will try to do this by for our hydrogen universe, for two very important classes of observations. One is the optical transitions like Balmer alpha, Leuven alpha, etc., as we have discussed. And the second one is this 21 centimeter line, which arises because of it's called a hyperfine splitting. We also have the fine splitting of the atoms. So that means that what I told you before of the hydrogen atom is actually not completely correct. We sort of knew this because we neglected that the electron had spin, we neglected that the proton had spin, and that actually induces small energy differences, small breaking of the degeneracy source of hydrogen. So to get a feeling for this, like I said, this is an order of magnitude now, semi-classical, if you will. We have the proton, we have the electron. But if we think about ores, where this, in a sense, in the classical way of viewing it, goes around the proton, it induces a magnetic moment. Yeah? Similarly for the proton, that will induce a magnetic moment. The proton here, okay? The energies involved for this moment then will be proportional to magnetic moment times the magnetic field. From Maxwell, we know that the scaling of the magnetic field is on the order of E and then V divided by C, Lorentz, which is then will be E R squared, the proton V divided by C. Now, for a dipole, this will be a dipole moment. Magnetic field is also, the scaling is mu divided by radius cubed. Falls off with radius cubed, okay? So, from this now, we can set up that the scaling of the energy here will be just, well, we have mu, and then we have b there, so that will be b squared r 3, but we have an expression for b there, so that will just then be E2, and then divided by r, v divided by c squared, okay? But then we're gonna go back and again appeal to our Bohr atom. If we look at our Bohr atom, I have to remember the expression. We know that if we put this at the Bohr radius now, there's a principal quantum number there, right? But you know that, then we had that the velocity was E squared over h bar for the principal quantum number n equals to 1, right? The radius of the Bohr radius was just h squared divided by E squared me, okay? So you can see I also have to look up these expressions, so you have them in the booklet, of course. And we'll also put up the scaling for the Rydberg. Here I just put it as a scaling, because again, I'm doing this in a brute order of magnitude estimate. Now, here, if we divide this by c, we have e squared divided by h squared c. This is a certain constant, which is called alpha, which has the numerical value 1 over 137. It is called the fine structure constant. Okay? So you can see that the scaling here goes with that fine structure constant squared, and then we have E2 divided by R, so we're just going to plug in the Bohr radius there. We get E4 divided by h squared me, but that's just the scaling of the Rydberg energy. Okay? So again, caveats here. If you want to calculate this precisely, we're going to have to, well, you would have to essentially solve the relativistic Dirac equation, alternatively derive a perturbation to the Hamiltonian there. But that's beyond the scope of this course, of course. We're interested now in understanding, so to say, a little bit what this means. Well, we know already that the principal scalings of delta E for, say, the optical transitions, that is the standard ones that we have had, those were 13.6 electron volts. That is, they go with the Rydberg, and then it was like, 1 over 1 divided by minus 1 over 4 or something like that. So, but the characteristic scaling was with the Rydberg, okay? Then we have the N. So what you can see there for this is that for the fine structure levels, they go with the Rydberg times alpha squared, which is then on the order of Rydberg 10 to the minus 4. This is 1 over 137, so squared would be there. So this means that the order of magnitude energies for the fine structure levels, transitions, they will be on the order of 10 to the minus 4 times the optical ones that we have discussed so far. So much, much smaller. Now, of course, I told you we were interested in the 21 centimeter line. That actually is the so-called spin flip radiation. So that then comes from, this is essentially then the spin orbital coupling. Yeah? So the orbital angular momentum with the intrinsic or the spin, electron spin angular momentum. But the 21 centimeter, that comes from the coupling between the spin of the electron and the spin of the proton. So a spin-spin interaction. Essentially, it's when they're aligned like this, and then when the electron flips, you emit a photon of 21 centimeters. So then they scale with the same thing here, only that we have to exchange the electron mass for the proton mass. So the delta E of the hyperfine splitting, as it is called, scales with R1 alpha squared, and then with ME divided by the mass of the proton. So that's then another 10 to the minus 3. That's roughly the difference. So that will be R1 times 10 to the minus 7. Okay? So if we now take, for example, then delta E, hyperfine structure, is going to be roughly delta E optical times 10 to the minus 7. And for the delta E optical, we had that it's on the order of 10 electron volt, that's Lyman alpha. But of course, we can just turn this around to take the wavelengths instead, right? We know that the delta E, the energy transitions, are just hc divided by lambda, yes? So we can say that the lambdas for the hyperfine structure levels are on the order of lambda times 10 to the 7. So a typical then hyperfine structure in this would be an optical wavelength that's 10 to the minus 5, 10 to the minus 5 centimeters, right? 10 to the minus 5 centimeters, that would be how many angstroms? 1,000? 1,000 angstroms times 10 to the minus 8, that's 10 to the minus 5, right? So 10 to the minus 5, 10 to the 7, that's going to be on the order of 100 centimeters. So that's the basic reason why they lie where they are. As you can see, you don't get so close, but that's because of the brute approximations I've done in order to derive. The important thing here is that you have these two principal scalings. The energy difference goes with the fine structure constant squared. Yeah? And then for the hyperfine also with the ratio of the electron to the proton mass. And that's then why they have so much smaller energy differences, or, if you will, so much longer wavelengths. Now, in that sense, like I said, the 21 centimeter line of hydrogen, probably the most famous line in all of astronomy, is because of this fine structure flitting. It is indeed when the proton here has spin up, the electron here has spin up, and then we get a transition to this one has a spin up and this one has a spin down. And that corresponds then to the emission of a photon with 21 centimeters, or the corresponding delta E that you could just revert from the formula. Yeah? Now, in this sense, for the book, just for the bookkeeping for you, when if you look at spectroscopic stuff here, you can see that technically now we're actually dealing with 3 types of angular momentums, even for hydrogen, right? We had the orbital, that was our L. We had the electron spin or electron internal. Normally goes with that, but now we also put it as minus. We put the spin of the proton, which normally goes by I. So the quantity that is really preserved is the total angular momentum, not the individual. It was just that we have neglected these so far. So in this case, often what you see is that the total orbital plus spin is denoted by J, which then is L plus S, and this total is denoted by F, which then is I plus J. So if you have now this, if, for example, this state now corresponds then to state of spin up, which is 1/2. Well, one of them corresponds to the state of L equals to 0, the ground state, and S equals to 1/2, right? That means that J equals to 1/2, okay? And this spin, so would be 1/2 then. So F would be 1/2 plus 1/2 equals to 1. The other one then would correspond to L equals to S, but S equals to minus 1/2, meaning that J would be minus 1/2, or F equals 1/2 minus 1/2 equals to 0. So this transition then corresponds to the F equals to 1 to 0 transition here, when you calculate it like this. Right. We will come back to the 21 centimeter, and I will just sketch out at the end a little bit of a fun thing that we have deduced from it in astronomy. Famous result. But first I actually wanted to take this now and do another order of magnitude estimate with it, which is sort of interesting. And that is that now we have something which is essentially an excited state, and it goes to a less excited state, reacts by emitting a photon, okay? So remember, classically, we could actually, when we did this in the classical way, we found a half lifetime, a typical lifetime of the excited state that was extremely small. It was on the order of, we can go back to our chapter 4 to see the exact, but it was something like 10 to the minus 9. Now I wrote 2 times 10 to the minus 9. Not sure it was exactly that, but we can go back and calculate it, right? And that came from the fact that we said this was a strange thing. In classically, all lines, because we had the one expression of the damping coefficients, had the same lifetimes, the same typical strength. Okay? But this we knew wasn't true. And we can actually deduce that just from, go back. Delta E, okay, of course then has to be on the order of this half lifetime times the emitted power, okay? Power is energy per unit time, right? And then times the half lifetime, that is our that. And this we know now is h nu, where nu is then, or hc over lambda. Now we're using nu. Could have used omega, h bar omega, if we wanted. As you wish. So in this case, we see that tau h nu divided by the emitted power, but the emitted power we had from the Larmor formula. Remember, for the optical transitions. The Larmor formula then was 2, 3, and then we had the charge, which now is an electron, c dot dot squared divided by c cubed. Let me see if I got that right. Where we also write this as 2, 3 d dot dot squared divided by c cubed, where d is the electric dipole moment. So these allowed transitions, they're electric dipoles. Yeah? Now, the question is, what is cc in this case? Well, c dot dot we knew was roughly c divided by omega squared frequency, which then, for this case, is going to be roughly the radius, right? Times 2 pi nu squared. You can set this to the orbital radius. And then if we plug this in here, you see that the typical lifetime scales as, well, we have some constants here, and then we have 1 over R2 nu cubed. Okay? So, if you now, we have the values, and now you can plug in the values yourself for tau, hydrogen, Lyman alpha. Our standard. We always go to Lyman alpha. And if you do that, you will get out on the order of 2 times 10 to the minus 9 seconds. That means that the Lyman alpha line is called a resonance line because it's fairly close to the classical value. It's a little bit higher actually here, so this is probably a little bit lower over there. You see that it has the Lyman alpha line has an extremely short lifetime in the upper state. Okay? Interestingly here, and this is a prelude for what we will do later, is of course, well, we knew that this tau was actually 1 over the damping coefficient, right? And now we have a way to compute tau, so it means that we have a way to estimate the damping coefficient. This damping coefficient, or the lifetime, we will also associate with what is called the Einstein A coefficients. And if we can get those, we will show this when we get to that section. We will actually study Einstein's original paper from 1914, yeah, in German, if you will, or perhaps a translated version. The thing is that then you can get the transition probabilities, not just for the spontaneous emission, but also for the absorption rate, and we can deduce that there exists such a thing as stimulated emission. But that's a little bit of a teaser for what we will do then. And that we can use directly then into our actual, say, radiative transfer calculations. Now, what we can interestingly see here for the half lifetimes is that if this is the scaling, then we can scale the optical transitions. So, for example, now, if we're interested in the Balmer alpha, right, that would be the 3 to 2 transition. We can scale this to the 2-1 transitions, right? Then we see that the scaling, if we put it in wavelengths, will the scalings will be the radius inverse, and then lambda is on top now, so it will be lambda 3,2, lambda 2,1 to the third power. Now I use wavelengths because we know the wavelengths. And then the radius inverse, so it will be the radius of 2,1 there, so radius of 1 then, radius 2 there, squared. So you can see that the half-lifetime then for hydrogen Balmer alpha, H alpha, is going to be, we know the wavelengths, it's 650/62, right, divided by 1216 here, 3, and this is then 1 over 2, right, because it's 3 to 2, so this is 2, this is 1, so this is 1/4, yeah? But this is on the order of, say, between 5 and 6, right? And divided by 4, so this is going to be on the order of 10. So that means that the half-lifetime of hydrogen H alpha is on the order of magnitude higher than the lifetime of Lyman alpha. And that's what sets essentially the strength of the spectral lines. But now look at the 21 centimeter line. Now, the thing with the 21 centimeter line is that there we have to do another scaling, and that is that it's not an electric dipole, it was the magnetic dipole. And the magnetic dipole scales with that times this fine structure constant. So if we want the tau 21 centimeter divided by the tau, say Lyman alpha, then we will get one over alpha squared, because the dipole enters as a squared, and then lambda 21 centimeter, or the mu, if I call it the magnetic dipole, that, and to the third. Yeah. So in this case, what does this mean? Well, it means that the half-lifetime for the 21 centimeter line is going to be, well, this is on the order now of 10 to the 4, right? A little bit more, but on the order of 10 to the 4. This is 21 centimeter divided by, yeah. Well, we can just plug in the numbers, okay? I'm going to plug in the numbers now. I actually did the calculations. So the lifetime of the 21 centimeters line is on the order of 2 times 10 to the minus 9. That was the lifetime of alpha, right? And then it's times 137 squared times 21 centimeter divided by 12 16 angstrom cubed. So here you have to translate this to there. And that's on the order of 2 times 10 to the 14 seconds, which is on the order of 6 million years. The real value, as calculated from detailed quantum mechanics, is on the order of 10. Okay? So we get almost within a factor of 2 by our simple order of magnitude estimates here. But the key thing is not really if it's 6 million years or 12 million years. The key thing is that for the excited state of the optical transition, that is the Lyman alpha upper state, n equals to 2, the half-lifetime of that state is 10 on the order of 10 to the minus 9 seconds. The half-lifetime of the upper state in the spin-flip transition is on the order of 6 million years. So translated into Einstein rays, or the strength of the spectral line, this means that this is an incredibly weak line. But the thing is here that the universe is so big and that there is so much neutral hydrogen around that we still see this line in a lot of places in astronomy. It's a dominant source of information in the interstellar medium. It's critically important when you try to map out the early universe from the era of recombination to the era of reionization. Again, we'll come back to those terms. And it's the critical component in determining the spiral curves of, no, the rotation curves of spiral galaxies. So that's what I wanted to take 5 minutes now at the end to discuss as an application of this 21 centimeter line, which we have learned the scalings for here. Now, imagine you have a spiral galaxy. It's easier to take an external one, you know, because again, if we're viewing ourselves inside the Milky Way, right? I sometimes make the analogy like some things we can see very clearly, but other things is very difficult. It's kind of like sitting inside the house and trying to observe things. I can see very clearly details here in the classroom and of you, you know, who looks happy, who looks who's sleeping, etc. But it's not so easy for me to deduce what's the color on the roof of the building. Right? I can see the ceiling, but if I'm going to see the roof, it's like, yeah, can I reflect that in the window? And then you can put up a mirror. It's not easy, huh? So some things are easier to observe for external galaxies. Yeah? And rotation curves are actually one of those things. So you have a spiral galaxy here, okay? And say that there are stars here in the disk and out, okay, that emits a visible light until this. Yeah? Now, neutral hydrogen clouds exist here in the interstellar medium, but they also exist outside of this disk, you know, perhaps above, perhaps below, or perhaps here. I'm just going to draw them here, right? So it means that these hydrogen clouds, they emit then in the 21 centimeter line. So if we can observe them, we can get an estimate. And then, okay, if we observe this galaxy and we take care of the projection effects, we know they rotate, right? That's what we're interested in, the rotation curves. So this will rotate there, this will rotate there, and then we measure 21 centimeter lines here and also outside the visible disk, there and there. And then we see how much red and blue shifted they are, and from that we deduce the rotation rates. And then we can plot that like this. So this would be the distance then from the center, and this would be the rotation speed. And then what do we expect? Well, as long as the disk, you know, is fairly there, then we would expect something which, well, goes up, or we can call it like a constant, but it goes up. But then we will quickly add, and then we will expect it to fall off. Now, why is that? Well, it has to do with the simple, if you think about then, again, your orbital motion. It's the same as we have used also in this course, right? But here would be that you have your G, and then you have your M enclosed within a certain radius r here, right? R squared, and that's the balance then by the centripetal force, yeah? So this would be the rotation here. So you can see that the rotation is going to be proportional then to the mass enclosed by that radius divided by r square root, yeah? But of course, if the visible mass, and here is the point, right? The visible mass at some point will vanish because there aren't any stars outside here. Then after that, you can treat that when you go far away, you have to go further than this, right? The board is not enough. As that there is no more mass, so that m of r is a constant, it's just m. And if m of r is just a constant m here, and you don't have any mass outside, no significant mass, it's dominated by that, then you can see that the rotation curve, of course, will then just fall off as 1 over square root of r. This is the same as the Kepler law. In the solar system, all mass almost is positioned at the center, because all mass sits in the sun. So that the rotation curves of the planets, they follow Kepler's law, 1 over square root of r. And that's what's expected when you go far outside of the disk. And you can measure that by the 21 centiliter lines. But observe, that's not what we see when we measure these. Rather, we see this. Very far out. Actually, it's very seldom that we even observe the downturn. So as far out as we can observe, they seem to be flat. And what does that indicate? Well, you can just look at this. It indicates that the actual mass of the galaxy still increases with r, because that's has to cancel. And if the mass of the galaxy still increases of r, but we don't see anything, because these hydrogen clouds, even though they're there, you know, they're very small in terms of the total mass. Yeah? They don't weigh much as compared to this gigantic disk in the middle. Huh? But there is a lot of mass out here that is invisible to us. Okay? And that, of course, the invisible mass is the key, one of classical evidence for dark matter in the universe. It wasn't the first, and it's certainly not nowadays the only. And again, this is something that during the spring we will discuss much more. And there are other indications from various branches of astrophysics, all pointing to the evidence of a lot of non-luminous matter, dark matter. In fact, the galaxies, in this case, or galaxy clusters, the large scale being dominated by that invisible dark matter component. But the most classical evidence for it, I would, in my own personal opinion, argue that it comes from these rotation curves of the spiral galaxies. And these rotation curves are inferred by the Doppler shift and the observations primarily of these these neutral hydrogen clouds at large distances from the disks in the spiral galaxies, emitting in this spin flip hydrogen line of 21 centimeter with, you know, mean lifetime of 10 million years. So we have to have a lot of hydrogen there, which we do because the universe is such a big place. So even if the density is low, this results in a significant amount of emission, which leads then to the inference of dark matter in the universe. All right, very good. that was it for today.